Hey everybody, this week we are going to be talking about stars. And we're going to start by talking about the nearest star to us, the sun, which you can see right here behind me. This video is showing our sun in many different wavelengths of light. So each one of these wedges is a different wavelength of light. So we know that the sun emits light in all parts of the electromagnetic spectrum. What we see in the sky is just what we can see with our eyes, the visible part of the spectrum. Now, some of these wavelengths of light, yes, we cannot see with our eyes. This one in particular, this one that is looking like this sort of yellow slice here, this is not what the sun looks like in a yellow color. Okay, this is what the sun looks like actually in X-ray or extreme ultraviolet wavelengths of light. And so whenever we're making these images, we just put on a color on them to make them look a little bit more interesting rather than showing them to you in black and white. So that sort of yellow wedge that I was highlighting earlier corresponds with this image right here. It's what the sun looks like in a wavelength of light that we call 171 angstroms. This little A with the dot above it, angstrom. 1 angstrom is 0.1 nanometer. So if we have 171 angstrom, that's 17.1 nanometers. That's a really short wavelength of light. That's much shorter than the purple end of our electromagnetic spectrum and the violet end of our electromagnetic spectrum. So this wavelength of light that we're looking at here is well beyond what we can see in the ultraviolet part of the electromagnetic spectrum. So above ultraviolet and getting close to the X-ray part of our electromagnetic spectrum. But we just give it a golden color just to make it look a little bit more interesting. So this particular image here, which is in the same wavelength of light as the image behind me, is showing us parts of the sun's atmosphere that emit light at 17.1 nanometers. But also, this part of our sun is incredibly hot. Remember, the things that emit light at shorter wavelengths, higher frequency, tend to have higher energy. So that part of the sun's atmosphere is actually a lot warmer than the sun's surface. So this image here shows us parts of the sun's atmosphere that are achieving temperatures of about 600,000 degrees Kelvin. Okay, so the peak wavelength of light for our sun from Wien's law, if you remember that from earlier in the semester, is about 500 nanometers. But again, the sun is emitting light across a broad range of wavelengths. And different wavelengths of light probe different parts of our sun's atmosphere, which again, we're seeing different parts of the sun's atmosphere by looking at different wavelengths of light right here in this image. The sun has a variable temperature. It's much hotter in its interior than it is at its surface, and then it gets hotter again above the surface. But the sun's surface temperature is 5,800 Kelvin. And the sun is the only celestial body in our solar system that emits visible light. So that means that everything else in our solar system, planets, comets, asteroids, are all emitting light in different parts of the electromagnetic spectrum that are not in the visible part. Mostly those other objects have lower energy associated with them. They're not as hot as the sun, and they'll be emitting light more toward the infrared wavelengths of light and longer. This is an actual spacecraft observation taken of the sun in our 171 angstrom wavelength of light, and you can see these big loops of magnetism attached to the sun's surface. These are loops of magnetic field. Our sun has a mass of 2 times 10 to the 33 grams, a radius of 7 times 10 to the 5 kilometers, an average density of 1.4 grams per cubic centimeter. Water has a density of 1 gram per cubic centimeter. So the sun's average density is more than that, but different parts of the sun's atmosphere achieve different densities. So the surface temperature is around 5,800 degrees Kelvin. Our sun has something called a luminosity. We'll learn more about luminosities, but that's how much energy per second is the star outputting. And for our sun, that's 3.8 times 10 to the 33. This is a unit called erg. It's a unit of energy over seconds. If we think about just the total number of atoms in the sun, 94% of those atoms are hydrogen atoms, and 6% are helium atoms, and the rest is everything else. But if we think about the sun's composition just in terms of mass and not the number of particles, by mass, the sun is composed of about 75% hydrogen and about 25% helium and a little bit of other things. Our sun has an interior structure. So just like how our planets have interior structures, the sun does too. But none of the sun's interior is solid. It's all a gas. It's all mostly hydrogen and helium. Okay. So the inner 25% of the sun by radius is what we call the core. And that's where the sun generates its energy by nuclear fusion. And then in the upper 25 to 70% of the sun by radius is what we call the radiative zone. Okay, that's part of the sun where the energy generated in the core is carried outward by radiation. So basically, a bunch of photons have a lot of energy. Photons are individual packets of light. They bump into each other in sort of a random walk process, and they do that, and then they work their way out of the radiative interior of the sun to what we call the convection zone. The convection zone by radius starts at 70% of the sun's radius and then goes up the remaining of the way to the surface. So essentially the outer third of the sun, or not third, the outer 30% of the sun is what we call the convection zone. Here, energy is carried outward by convection. So in this zone, the material is getting hot at the bottom because the radiative zone right there, okay? That material is rising to the sun's surface, cooling, and it turns over again, and it sets up these large convection patterns like what we talked about in the interior of Saturn and Jupiter. And then we have a region called the tachocline, which is the interface between the convection and the radiative zone of the sun. And then the surface of the sun is what we call the photosphere. Now, it's not a surface that you can stand on, okay, it's still a gas, but that's where we define as the edge of the sun is the photosphere. Stars have a particular structure that is dependent on their mass. And our sun has this radiative interior and then an outer convection zone. Now, stars that are smaller than our sun, a lot smaller, don't have any radiative zone, and they're fully convective. And stars that are much bigger than our sun, bigger than 1.5 times the sun's mass, have a convective interior and a radiative outer shell. But anyway, wherever you find a convection zone of a star, that's where you expect to find magnetic fields. And so we'll talk more about the sun's magnetic fields too. At first, it was thought that the sun was on fire, like a giant piece of coal or a wood, something burning like a wood fire. But if this were the case, then our sun would have lasted only for 10,000 years. And we know that it's been here much longer than that. We've been here much longer than that. It's also suggested that if it was still gravitationally collapsing, still collapsing in on itself due to its gravitational pull, it could produce the amount of energy that we see of the sun. But if that were the case, if the sun were only powered by it collapsing on itself because of its immense gravity, the sun would only shine for 25 million years. And we've already learned that our solar system is much, much older than that. But what if the sun were powered by nuclear energy? The sun could sustain its energy through nuclear fusion for 10 billion years at its current luminosity. The sun is about halfway through its lifetime. So our sun is about halfway through its lifetime of around 10 billion years. So our sun is actually generating its energy through nuclear fusion. So what's going on in the sun's interior? What is this nuclear fusion thing that I'm talking about? Well, the interior of the sun is really hot, about 15 million Kelvin, and it's under extreme pressure too. And under that extreme temperature and pressure, the sun releases energy by fusing 4 hydrogen nuclei into 1 helium nucleus. And whenever it does this, that process releases a lot of energy. That's the energy that's fueling our sun. So here's a plot that shows the temperature of the sun by radius. Calculations show that the sun's surface temperature and density increase as you get closer and closer to the core of the sun. So let's say we start here at the sun's surface. we have a temperature of about 6,000 Kelvin. Earlier I said 5,800 Kelvin, but roughly, okay? As we get closer and closer and closer to the interior of the sun, the temperature increases and increases and increases and increases until at the very core of the sun, we have reached a temperature of 15 million Kelvin. Okay, as we do that, the density inside the sun increases too. I said earlier that the average density of our sun was about 1.4 grams per cubic centimeter. The density at the sun's surface is about the same density that we find at sea level on Earth. But in the interior of the sun, the density is about 100 times that of water. The photosphere is what we define as the sun's surface. Although since the sun is made up of hot gas, it's not really a surface, okay? It's just where we consider the boundary of the sun itself to be. For light to transmit through the solar atmosphere, this light has to come from a region with what we call an optical depth, near something that we call tau is equal to 1, an optical depth of tau equal 1. This is the little fancy Greek letter tau. At the optical depth of where tau is equal to 1, this is the place where about 50% of the sun's light will escape. Above the photosphere, the atmosphere of the sun is optically thin. That means that most of that light is going to be able to escape very, very, very easily. But below the photosphere, the sun is what we call optically opaque. That means that the light is not easily able to escape from regions of the sun below where we say tau is equal to 1. So essentially we're defining the surface of the sun as the region where 50% of the sun's light is able to escape easily, and 50% of the sun's light is not able to escape easily. So when I say opaque, opaque is something that you can't easily see through. And something that is, optically thin, something that is not opaque is something that you can easily see through. So here is what we define as the photosphere with the optical depth of tau is equal to 1, calling that our sun's surface, okay? And so everything below that, closer to the sun's interior, is what we call optically thick, okay? More than 50% of the light is not able to escape from whatever region that is, okay? Above the photosphere, that's the region of the sun's upper atmosphere that we consider to be optically thin. More than 50% of light is able to escape from those regions. So you can peer through much easily those upper layers of the sun before you get to the photosphere. We can image the sun's photosphere. The photosphere shows us evidence of the sun's convective nature. And here's a telescope image taken of the photosphere. And you see these sort of little cellular boundaries here. We've got these brighter pockets surrounded by these darker lanes on the ends, okay? Well, these are what we call convective granules. And these are regions where the sun's warmer material from inside are rising to the surface, cooling, and then turning back over again. And then that material on the edges is sinking back down towards the middle or towards the interior of the sun. Now these granules, they're changing all the time in shape. And a typical granule has a lifetime of about 5 to 10 minutes. They're very short-lived, and they're about 1,000 kilometers across. So they're actually pretty large in general. So if we zoom in on one of these granules on the photosphere, here's what it looks like. You've got hot gas from deep inside the sun rising to the surface. It cools when it reaches the surface, and then it turns back over again. So the hotter gas is in the middle. That's the part that glows. And then the cooler gas on the sides, it meets up with the cooler gas from the other granules nearby it. And then that cooler gas comes together and it starts to sink back down again. So when gas is colder, it sinks. When gas is warmer, it rises. And so that's what's happening here. Warm, hot gas rising, cools off, and then the temperature is less, it's heavier now. If something is cooler, it's also more dense. And then that material is going to sink back down. Since it's a little bit cooler, that's why those lanes on the edges of these granules are dark. Okay, and we're going to see some more images of this in a minute. There's an entire study of the sun called helioseismology, which studies oscillations of the solar surface caused by interior convection. So you can think about helioseismology like how you think about seismology on the Earth. Okay, seismology on the Earth, people use that to study what's going on inside the Earth, and also, you know, to learn more about earthquakes and that kind of thing. So the sun has quakes too. Okay, it's constantly kind of vibrating, and you can essentially think about it as like ringing a bell. When you ring a bell, what's happening is that the sound waves are traveling inside the bell, and that's what's creating the sound. Okay, inside the sun, the motion of the gas inside the sun sets up wave patterns of sound, and that constantly moving around inside the sun, kind of like a bell. And the end product is that essentially the sun kind of vibrates or pulsates a little bit. And you can study that with a process called helioseismology. And studying that more in detail actually helps us better understand the sun's interior structure. Here's another picture again of granulation. So we've got convection manifesting itself on the photosphere, on the sun's surface. And we've got a bunch of these bright convective granules surrounded by the dark, narrower lanes. That's regions where the material has cooled off and it's sinking back down towards the interior of the sun. The region above the photosphere is called the chromosphere. It extends from just above the photosphere to about 10 to the 4 kilometers above. It is optically thin, so it's easy to see through. Its density is 10 to the minus 4 times that of the photosphere, so much less dense. And it has temperatures of 15,000 Kelvin. So remember, the sun's surface is about 6,000 Kelvin. So once we're getting above the sun's surface, we're starting to heat things back up again, which is a little bit confusing. The chromosphere is named because it is dominated by emission lines. We talked about emission spectra. It's dominated by emission lines, and in a particular emission line that we call H alpha, hydrogen alpha, which has a wavelength of 656.3 nanometers. The chromosphere is named for the rosy red color, the 656.3 nanometers, visible only during eclipses. So this is the red part of the visible spectrum. And so the chromosphere, chromo means color. So you can see this part of the sun's atmosphere in color whenever we have a solar eclipse, a total solar eclipse, when the moon passes directly between the sun and the earth. So here is the reddish hue of the chromosphere seen during an eclipse.